Well, welcome to this video. In this video, I will be talking about some basics about a general circuit of stabilizers and also discuss the quantum error correction conditions. And this quantum error correction condition will help us in building up error correction criteria for stabilizers formalism also. So the main idea is what I am showing it in the circuit and what we have seen continuously in the previous videos. The idea is you have input as k different qubits, and here this is k what I am showing, and you also have register qubits, and this is shown by 0r, and this register qubits, they are n minus k, so that the total physical qubits that goes into the encoder is n. So here I am showing that with a n, and then there is k logical qubits. So this is logical qubit, the logical qubit. The first one is number of physical qubits, and last one is the number of errors, the minimum size that goes undetected. So I have an encoder, and then I have an error channel which is shown by E, and then I have a set of stabilizers. So these for example can be Z1, Z2 and Z2, Z3 for the case of bit flip error, which we saw as it was a 311 code, or it can be other various stabilizers that we saw, but there are a lot of number of them, so we are trying to generalize the circuit, and then each of the stabilizers commute with one another, so they can be measured independently. So this I have shown by this syndrome extraction circuit, which is basically this entire circuit here. So this has n minus k zeros as ancillary bits, and then there is one Hadamard gate, and then you have the conditioned operation, and then you again have Hadamard gate, and then you measure the qubit. So let's look at what happens if I measure one of the stabilizers. So suppose I have the 0 I, so it is measuring the ith stabilizer. If you look into the circuit, and also if you follow the previous discussions, it's easy to see that the final state for this single stabilizer is of this form. It is E psi L 0, which is having a prefactor of 1 plus Si, and it has 1 minus Si with 1 in the ancilla. So this is interesting because now if my error and Si, the ith stabilizer, anti-commutes, I will register a 1 in the ancilla. So this is what was happening throughout all the codes that we have seen so far. What was happening was that the stabilizers anti-commutes and generates a syndrome of +1, and this is what we see. So this is something that happens when you choose the code space in a very specific way, and you can only correct certain types of error. And now we will see which types of error can be corrected and which types of error cannot be corrected. So this goes under the name of quantum error correction conditions. So suppose I have a qubit, a set of states psi L that belongs to the code space. So this is the logical state, and now I put it through some error channel which has some errors. So it will introduce errors in the qubit or any state that is in the code space. So the code space need not be two-dimensional. And then there is a detection part, which is the syndrome measurement, and there is recovery part also, where you apply the stabilizer again, or you apply a inverse of the operation to get the correct state. So the detection plus the recovery part can together be clubbed as something called as error correction operations R. So R is kind of standing for recovery, but it also has the detection included inside. So based on this, what we can say is that if my state is in the code space, or it has support in the code space, so here what is support? Support is nothing but the span of the rows. It forms a subspace of the code space. So this is important. And if my space has support in the code space, then if there is some error and then there is some recovery, what I would want is basically I get back my original state. So this is what we would expect out of error correction conditions, that it will provide us with a set of conditions on the error channel such that recovery is possible. So I am not talking about recovery of any state. What I am talking about is recovery of states which are in the support of the code space. So here I have formally written the error correction condition, and we are going to prove this. So the idea is, if my cross operators for a given channel, they satisfy this particular condition here. So this is the condition. If my cross operators satisfy this condition, where P is a projector onto the code space and alpha ij is just some Hermitian matrix elements, and if the left hand side and right hand side, they are related in this particular fashion, then I can say that there exists a recovery operation for the error on the code space. So what this means is that, in a different way, what I can do is I can take this equation, which I denote by star, and then I calculate the matrix element of this equation on the code space, and the code space is denoted by C, which is span of phi L. Then the matrix element on the if I just squeeze it on the left hand side by phi k and phi L, then I will get a delta KL, because the code space words are basically orthogonal to each other, and the projector acting on the code space keeps it invariant, so the projector gives us phi L only. So P acting on phi L is equal to phi L, and similarly phi K, P is phi K. So using this, we can also frame the condition in a different way that I am showing on the screen. So now let's go to the proof of the statement. So this statement is also called Knill-Laflamme conditions. So this is basically the condition that the projector and the cross operators must satisfy this kind of a relation. So for the proof, we start from the fact that alpha is a Hermitian matrix, so we can diagonalize it and let U be the matrix, unitary matrix that diagonalizes alpha. And suppose now what I can do is I can define a new set of cross operators utilizing the unitary freedom in the cross operator. So what I can do is I can use the U that diagonalizes alpha, and I can rotate my initial cross operators to define new cross operator Fk in this particular fashion. So once I have Fk, now what I can do is I can calculate this particular quantity, that is projector times Fk dagger, Fl, and projector again. So P stands for projector onto the code space. Now I can simply plug in the Fks and Fls in terms of E, the cross operators Ei and Ej, and this gives us a simplified form, that is dKl times P. So the first equation that we get is P Fk dagger FLP is equal to dKl times P. So this is the first equation. And now what we do is we take this particular operator FLP, and I have just renamed the index as K, and FKP, what we do is we perform a polar decomposition of this operator. So if we perform a polar decomposition, we will get some UK that depends on the subscript K, and then we can write it in this particular fashion here. So what we have done is we have simply taken FKP and performed a polar decomposition to get under root DKK UKP. So this is simple to check, because FKP, Fk dagger, FKP, this is same as DKKP from 1. So here we are using the condition 1, and because P square is equal to P, so under root of P will have the same spectrum as P, because the projector always has 0 and 1 as its eigenvalues. So with this we will have now a set of orthogonal projectors P. So what we are doing is we are constructing a syndrome measurement and a recovery map R, so that it can recover our original state from the errors. So we are using the information of the error to construct these projector operators pk such that they are rotated form of the projector onto the code space. So this is the second important equality. So this can be written as fkp uk dagger over under root of dkk. So this is again simple to check because ukp is same as fkp over under root of this by using this. So we are using this in here. Now let's come to the fact that these are orthogonal projectors. So this means I am rotating my code space into error spaces which are orthogonal to each other, so that I can basically correct them using the inverse of uk. So pl pk is pl dagger pk. This is simply the property of the projector operator. And now pl dagger pk can be written from this two part here. So from here I can write pl dagger pk, and then this will be 0 because l is not equal to k, and this entire thing gives us the diagonal element. So if you see this thing, it is equal to this particular dkl times p, and dkl for k not equal to l is 0 because this is a diagonal matrix. And so pk and identity minus sum over pk to make a complete set is what we call syndrome measurement here. And now we can explicitly write the recovery map. The recovery map is simply r of sigma, that is you first use the syndrome measurement pk and then corresponding to pk you apply uk dagger, and then sigma is epsilon of rho because sigma is the error state that we have, and this can be written in this particular fashion here, where we have simply used the fact that epsilon has cross operators fl, and that's how fl comes. And now we have written rho as under root of rho two times, and now we will focus on this side and how this can be simplified. So u dagger pk, so I am in this line here, so this is the part. So this can be written as, I just write under root of rho as p times rho because rho is in the support of the code space, so p is like an identity on the code space. And then what I do is, from here I know I will use the number 2 operation here. So I will write pk dagger in terms of p and uk. So this is what I have used here. And then what we can do now is use the equality in 1. So let's come back to 1. So 1 says that fk dagger fl acted by the projector gives us dkl times the projector. So this entire thing we can simplify. We can write it as dkk times delta kl because of the diagonal elements, and this is what we get. So what happens to the denominator is that it cancels out. So this is equal to delta kl times dkk, and the denominator has a under root, so this becomes under root here. So one of the roots cancel out. Now let's look at the inverse condition. So what we have done here in this entire proof is we have simply said that we can construct a particular syndrome measurement and recovery protocol given an error that affects our code space in a particular way. So from here what we do is, now we go to this side, which is basically for any state. What we have to show is r of epsilon. So the idea is if it satisfies the property that the recovery, so R of epsilon of rho is proportional to rho, then I have to show that the particular conditions hold. So now we will do that. So for this it is simple that we take any state and then project it onto the code space. Then it will have a support on the code space, and then R of epsilon will keep this code space invariant, because this will be an error correction. So it gives us P rho P, and this proportionality is a constant independent of the state, because it's valid for arbitrary states inside the code space. Now what we do is we can write epsilon as EI, so these are the cross operators for epsilon. We can write the recovery operation as RJ, these are the cross operators, and on the right hand side we can write C P rho P. Now what we see is that the cross operators on the left side, which has these elements, are identical to the cross operators on the right side, which has only one element. Now from this you can deduce by the unitary freedom of the cross operators that the two cross operators, so I have done the small math here, but the main idea is that the two cross operator will be related in this particular fashion here. So RJEIP is UJI under root of CP. So from this what we can deduce is that this means that all my cross operators are proportional to P with the prefactors of UJI for some complex matrix. And now I can find the adjoint of this. So this is the adjoint, and then basically I am done with the derivation, because what I can do is I can take the adjoint and the original equation, and then I can sum over the k. So here I have taken the adjoint, and this is the original one that we found. So this is equal to UKI under root CP, and this is equal to UKI star under root CP, and now I sum over the k to get this particular output. So it is important to know that the recovery operation forms a complete set, so the cross operators are complete, but for the error operation it might be trace non-increasing only. So with this idea we can say that P epsilon I dagger epsilon j P is alpha I j P, where alpha is of this particular form here along with the summation. So alpha, so I have not explicitly written, so alpha I j is summation over k UKI star UKJ. So with this we are done with the proof. Now we will talk about discretization of errors, which is one of the important concepts that say that if you have a syndrome and a recovery for a particular kind of error channel, a lot of different error channels can be used with the same syndrome and recovery. So that's the basic idea. So overall what it means is that if you have a recovery channel for EI, then you can form linear combination of EI to get some different Fj matrix. Then for these Fj as cross operators, the recovery channel holds. So that's what I have written. If R corrects EI, then it also corrects a lot of different kind of errors. So now to see this, it is very simple to see this. We have to just use the proof that we saw beforehand. So from 3 what we have is that this particular condition holds, and we will use this particular condition. So you can see I have just written this condition here. So let's go back. So what I have written is UK dagger PK EL under root of rho is equal to this particular side. So this is third equation, and here also I have written the same thing. And now what I will do is I will write basically, so this is E, and now I have to write it in terms of F. So this can be written by simply substituting. So let's see. So if I write fj, I can take fj and write it as summation over I m j I e I, and then apply 1. So I will apply this here to get this particular line that I am showing. So basically so from here what we can do is we can write ROF. So F is the new error. It is simply nothing but you have FJ, and then you have the recovery channel, which is PK and UK dagger, and then it's a matter of just applying this. So I will apply this here to get this particular summation, and that will show it to be safe. So that's all for this video. So in the next video we will talk about error correction condition for stabilizer codes. So let's go to the next video.